Good morning. Sorry for being considerably late. I was told it takes 30 minutes with the cab from the airport. It took far over an hour. So maybe I should have arrived yesterday evening and enjoyed Paris. But there were some duties in Vienna. So sorry for being late. I'm a little bit introducing the robot. We don't have it yet, but we are one of the first ones to get it in Vienna, together with CNIS, so we are very happy about it, and our primary task actually is to make robots see. So I have a few examples on what we are doing, few actually from now that we hope to upgrade to Romeo, and a few that we have from other robots that we want to bring to robots. To give you a little bit about my background, I'm still dreaming that one day we just get the robot helper for our homes. We get the box at the supermarket, unload it. Yeah, and then we need to show the robot some things. For example, we need to show it the apartment, as you would show a guest around. Something I'm demonstrating here in a larger warehouse. You might guess, there's also one in Paris. So you would show the robot around like you show a person, maybe a little bit more specific to specifically learn it some places. You know, that's my bedside table. That's my preferred place on the sofa. So you should know about these places. And the same thing is true for objects. Yeah, you would need to learn it objects, particularly your favorite marks or other objects particular to your room, while you would still expect that the robot would know a lot about all the objects that would be in your home. I mean, the robot should know about chairs or tables, or it should know about marks, cups, plates, and so on. Yeah, so definitely there needs to be quite some knowledge in there, and of course it should know about navigation, which we are demonstrating here. And it doesn't have, this was only a mobile robot. Yeah, in the future I rather see it's going to be all these robots. That's the newest picture I have of Romeo, but I think there are newer ones. How do we approach that? It's going to be a very, very complex system. You know, walking or not, it's going to be a very complex system. How do we approach that? And at the moment we approach that and deliver robots, for example, this is test series in an elderly home, where already the system is very complex. We have nearly 100 components running in software on that system. So we need to make sure that we do the right thing. And what we really use most of the time is that the robot acts in an environment, and I know very much about that environment. So for example, I always assume there's some ground I can walk on or drive on. That's the very first assumption. And once I have that information, the next thing is, what do I find at the borders of the free floor where I can walk? Yeah, I find walls, I find chairs, and from this you can progress. It's unlikely that, you know, wonderful croissants will float here in the air. Yeah, even if I look for a croissant, I would rather go for a table first, or a shelf. Yeah, so there is some hierarchy in the environment that it's human-made. So it's made for humans, and I can exploit that. And that's exactly what we do. And one of the tasks at the moment, and that's the nicest example we have of a mobile robot with arm, is for elderly people. And in this case, it's really low cost. So that the robot is about 15,000 euros at the moment. And yeah, at the Vienna University, we put together 6 research groups and said, yes, we get Romeo, we want to investigate techniques for safe and social robotics. And the really interesting thing is it's not only technologies. Architects are very much interested on how could be the relation between a humanoid robot in your home and the people. How could you use it? What's the spatial relationships? So it was very interesting to us that they were very interested to use and apply the robot. And we are looking forward to get it soon. As I said already, the approach we take is what is called situated. So we situate the robot in the environment, and as it interacts with the environment, we use all the constraints we can get. So if whenever I orient, and I will have an example for humans, so if humans orient in that room, we do not do what robots nowadays do. Robots nowadays have a laser sensor down here, yeah, which takes some very special, you know, slice of the environment and then assumes that yes, this is a wall, this is nice, but then actually it would not see the legs of the metallic chairs here, but probably some legs of the persons, and that's it. Okay, so it has a very special picture, and this is used, these features are used to orient for a robot. That's the technique nowadays, but it's very opposite to what humans do. So if you enter the room, you immediately see that this is more or less rectangular, and as soon as I move forward, I expect the wall coming to me. You know, there are wonderful tests where it's shown that if this isn't true, you would be extremely surprised, and you can do that in simulated environments. And we orient, because it's rectangular, you can spin me around, get me out, blindfold me, whatever you want. As soon as I'm here, I take that rectangle again and orient. And there are some nice tests, which I have here data from children, but there's also some nice tests with adults. So as long as the average is 8 to 9, we can do that. So it's just, like 10-15% longer on one side. We immediately can orient because of that relationship. And that children can do that, with 2.5 years of age. That they orient because of that room structure. At that year, that there's an orange wall, you can tell the children they will not use an orange wall as a landmark, because that capability comes about 5 years of age. Yeah? So there's an underlying mechanisms of people on using this, and that's exactly our approach. If I want to orient, let's go for the walls first, the big structure first, and then I can go for the other structure. Yeah? Where's the floor, where's furniture, for example. Yeah? If I move, I need to have the floor anyway. If I search an object, I rather search on a table or a shelf than everywhere. Yeah? So I accumulate knowledge about the room. So how can you, for example, move this into a now? So we have that problem actually sometimes in soccer. In soccer it's relatively easy because you have only 2 goals, so it's like a 2-directed problem. But it's similar to that problem of the rectangular room, so which way I'm facing. And of course you use the environment. So we create, in this case, we create depths and color histograms of the surrounding. And wherever we look, we try to match that. Yeah? And of course you have a modeling a modeling phase first, where you orient and look around. That's exactly what I said. You get the robot, you put it out of the box, and you show it first. And from that point on, you can use that orientation all the time. Yeah? It would orient you in the big space, yeah, from seeing something in the far distance. And since you have so many features, it doesn't matter. Even if a whole group of people stands up and some features are blocked, it's very robust because I still see quite a lot of the background, particularly everything that is above head level. Much better than all these floor sensors that robots nowadays use. The next one is, of course, moving safely. I need to have the ground. Yeah, I mean, robots are expensive. I should not walk anywhere where I cannot place my foot. Yeah, so it's clear I have to do that. And there are now nice sensors, with any stereo camera or RGBD camera, Kinect camera, you can do that very quickly. I think in the moment we need 3 milliseconds to come to results like on the floor left. And you see already, that's perfect. That's my free navigation area. And already the next problem is solved. Where should I serve? Where in the image are tables, sofas, and chairs? It can only be beyond that, green line. It cannot be before. Yeah, so I have already very good indication to do the next step of image processing. Yeah? And actually the free room can be perfectly used for localization as shown here in an example on the right. Again, something from humans. So there have been some landmark experience by Michael Land in Sussex testing tea making. So you enter a new kitchen and what is the most British of all tasks? You make tea. But it's a new kitchen. So you don't know about it. But you have a very clear model of what involves tea making. Yeah, and it takes a human about 30 seconds in a new kitchen to adapt the model that you have. Where's the fridge, where I find milk most likely, where is the teapot, where's the water cooker, where's sugar. Yeah, one fantastic example, where's sugar, it's up on the shelf. The person, 30 seconds it takes, and you adapt your model to that kitchen. So you use a complete model of the task and what is involved in the task, and then deploy it in a new situation. And that's exactly what we want to model on Romeo. So the first thing, of course, is attention. We want to find where things are, where the structures is. I talked already about the walls. So whatever sticks out of the wall is important. Yeah, cupboards coming out, horizontal planes where things can be on. Even verticals for door handle, is perfect because door handles stick out. So this will attract our attention. Once I have that, many times it's relatively easy, as you see the right examples. If objects are not too cluttered together, I have nice chunks that I see on the table. Yeah, and then I come with my technique. For example, one technique, Either you learn many objects by examples, showing many examples. Very tedious job. Many master students had to do many learning phases. I had a clever PhD student. He said, no, we go on the internet. On the internet there are tons of 3D models of objects. We download the models. We see how they are similar. Chairs is really many. They are different, but you end up with, I don't know, 20, 25 is about what we have. Prototypical chairs. And then you learn models from them as you would see them, because you have the 3D model is a model from all around, okay? But you always see the object only from one side. Yeah, even the robot will never see that chair from the back. It's practically impossible to go behind the chair, so it will always see it somehow from the front. So I need to have a model and see it from the front. Yeah, so it might look like this one, for example. Yeah, any of these. Legs are very often seen, not very good visible. Yeah, might be a back there, Actually, you can do the same for any other object. We have at the moment 200 objects in the database, and create these views, and from these views you can detect that. And the nice thing is, you learned on a database, so even if learning takes some days, acknowledged, detection is very fast. So this is real time. Yeah? And the algorithm has never seen any of these specific objects. It just learned from data from the web. Yeah? We have sometimes some false detections, particularly if the arm goes in, because we separate from the plane and sometimes the arm still touches. But you see, even the orientation doesn't matter. Small rolling, no problem. That video runs very long, and I think I'm short of time, so if you want to visit, it's 3d-net.org. There's that video and actually some source code also for most of that, and all the training data. That was the raw detection. Very fast, as you see. Yeah, we have about half a second detection time. For the class, I don't know what object class I put there, and at the moment I have about 50 classes that are very reliable to detect. But what I can then do, because I detect exactly which model I got, I thought this is the best. I can fit this model onto my data and then confirm. So for example, we had big problems with toilet paper, in the center of the picture, where the percentage was actually much higher. 39% it's a bowl, 29 it's a mug, and only 25 it's a toilet paper roll. Yeah? But you use the models, you project them in the image, and then you try to fit. And if it doesn't fit, wrong guess. Okay, you try the next one. And then, green highlighted toilet paper. We were like 100% sure it's a toilet paper. Yeah, although this was only the third best guess. Yeah, so you can do quite a lot with a second, verification step. And then, of course, once you know what object it is, you can grasp it. I'm sorry, grasping is still one of our slowest procedure, but I hope with Romeo and the help of Jean-Paul Lemont and others from CNIS, we have some faster motions and faster path planning, which is not our task. So we used some tools from others. So you see in the left in the screen, this was the simulation. I think the task was to pick up the pineapple. So among the 3 objects, we detected the pineapple. And since you know it's a pineapple, you can sort it. Yeah, so fruits should go in the left red basket there, because you have information, you have semantic information about the object. The hand we are using is actually a prosthetic hand from a Viennese company called Otto Bock for humans who have lost their hand. It's actually not ideal for a robot because usually it's actuated by a human behind it, and we have only a robot behind it. It's not as clever, by far not as clever. Okay, you wonder what you do if you have clutter. In clutter it just takes longer. So there's a scene with high clutter and you have many more hypotheses and you just need to sort out which are the valid ones. Yeah, so again this verification step that you can do, and you see then, even then we find all these different types of bottles. What you do in real clutter, for example, this nice plate with all these croissants, could I pick the top one? And yes, I can. We never tried the croissants though, not such good ones in Vienna. But we tried scenes like this. Yeah, and there it turns out it's very useful to have this 2D and 3D information. Again, planar information or what is high up, because what is high up is easier to grasp. And if you have that, you can sort out clusters of objects. So there's just really a random pile of objects, and we can take whatever is kind of top, and wherever we see good grasp points. Yeah, so you see the big ball cannot be grasped from the outside with a hand, so I take the rim, I take this one, and so on and so on. Of course, in some situations, we do not clearly see that objects are separated because we do not recognize the objects. So I think the next trial will pick up two objects at one time, just accidentally. Again, no, this is not this one, it's the next grasp then. Again, you know, you put it down on the table, you could take it again, and at one point I'm sure you can be pretty sure it's only going to be one object. So sorry, one more time, one more grasp to wait. This was nicer to grasp. I mean, you saw it's a very nice parallel shape, so you could go for it. Yes, this is where robot picks up two objects. Yeah. Try it again. Sooner or later it would separate, and you could really hold the eye in the object in front of your eye and model it as we modeled the other objects from 3D data. And finally, once you have recognized that this is an object, for example, you found the mug, but the mug is lying on the side. Yeah, but you detected it's the mug, and you want to bring it and fill it with liquid. You know exactly what to do, because you discovered it, you know the pose of the object, and you know it can only contain water if it's upright. You know, so the detecting the object lying already tells you, no, I need to have a 90-degree turn in that direction. That's the action the robot needs to execute, and then you can already plan to grasp it the right way. Yeah, you need to grasp it from the top now and then move it to the side. Okay, we are very much looking forward to try all these things on Romeo. To study, but as of my aspect is particularly the vision aspects, bring it onto an embodied system, and of course to study together with the architects and the computer scientists the spatial and social role of a robot in a home. And I'm looking forward to collaborate with CNIS, particularly Jean-Paul Clement. Thank you.